It's a great pleasure to introduce Professor Madhusudhana as the first speaker of this afternoon session. Professor Madhusudhana retired as an emeritus professor at RRI in 2020 after joining the institute in 1971. Okay, so we have somebody who's really had a long association with RRI here. Along with Professor Chandrasekhar, he founded the Liquid Crystal Laboratory at RRI. He has given RRI and the physics community a legacy of scientific research on the physical studies of liquid crystals. In particular, he has done seminal work on liquid crystal phase transitions and has discovered a new liquid crystalline phase. From what my colleagues tell me, this is only a few of several important contributions that he has made. I'll give you a brief bio. After obtaining his PhD degree from the University of Mysore and a brief stint at as a lecturer in the physics department, he was invited to join RRI, like I said, in 1971. And apart from brief visiting assignments in Orsay, University Paris South, and Centre de Research Paul Pascal, his entire career rest of the career was at RRI until he retired in 2006 as Dean of Research. He has advised engineers of Bharat Electronics, I guess that is BEL, to develop know-how to manufacture liquid crystal displays. He's a fellow of the Indian Academy of Sciences and the Indian National Science Academy, as well as a recipient of the Bhatnagar Prize for Physical Sciences in 1989. He will be telling us about the evolution of the soft matter laboratories at RRI, and we're very honored to have him here with us, and I look forward to a very interesting talk.
Well, thanks a lot for that introduction, and I should thank the director for asking me to, maybe they know there is no collar mic, so I have to stand here. For asking me to give this talk. See, evolution always has a beginning, and as far as this campus is concerned, is that okay? As far as this campus is concerned, the beginning is always 1948, when Professor Raman started this as a private research institute. His first research student in RRI was one S. Chandrasekhar, whom he took in 1951, 3 years after he started this institute. Chandrasekhar measured optical rotator dispersion of several crystals, improved a formula to analyze for his PhD. And then after spending a few years in a couple of research centers in UK, I won't go through all that, he became the first head of the newly started Department of Physics in Mysore in 1961. And at that time, S. Chandrasekhar and D. Krishnamurthy, who had also been students of Raman at RRI, joined Mysore University as readers. All the three were my teachers in my MS. Chandrasekhar initiated research activity in liquid crystals, and I joined him towards the end of 1965 as the first PhD student on that topic. Liquid crystals, of course, were discovered in 1888, but the research work in that area had been on a low key, started to have a resurgence only in late 1950s. The simplest liquid crystal is called the nematic, which has a pure orientational order of molecules with shape anisotropy. Why I am telling the next thing is I am coming back to this point at the end of the talk. The first molecular theory of the orientational order was proposed by Max Born. Most of you are familiar with his name. In 1916, suggesting that the nematic was a ferroelectric liquid with a polar order of molecular dipoles as shown there. But then Ansager, another Nobel laureate, showed in 1949 that long hard rods undergo a first order transition from isotropic to the nematic phase as the density is increased. The increased translational entropy is more than the loss of the orientational entropy. It is a truly seminal paper because this is the first time anybody has shown that a phase transition could occur due to a competition between two entropies without any interactions. Of course, Mayer and Saupe showed in 1959 that anisotropic dispersion interactions give rise to the first order isotropic to nematic transition at some temperature. Now, of course, you can think of temperatures because there are interactions. Both the above results imply that the orientational order of the nematic phase is apolar and the order parameter is really a second rank tensor. And in fact, later the discovery of what is called phenyl, a lining up of 5 phenyl molecules without any net dipole moment, clearly showed that bond was wrong. Of course, in Mysore there were no experimental facilities, so we mainly did some theoretical work. For example, my thesis was on extending the Mayer-Saupe theory by including higher order terms to account for temperature dependence or order parameters of several compounds. In the 1960s, when we started work in Mysore, only 4 types of liquid crystals were known. I have already talked about the nematic, which is this. If the molecules are chiral, that is, lack a mirror symmetry, then the average orientation direction twists around an orthogonal axis. Oh, sorry, did I press the... And you get what is called a cholestric phase with a pitch which is of the order of the wavelength of light. In fact, the first liquid crystal was discovered in cholesterol benzoate back in 1888. I think I keep going back to, sorry. I don't know why this doesn't, where should I point? Here? It's not going back. Now it has gone back, sorry. If the phenyl had 2 long chains attached at both ends, then it becomes biphilic in nature. There is an aromatic core and aliphatic chains. That will produce what is called a spectic liquid crystal. And if the long molecules are roughly along the layer normal, it's called a smectic A. And if they are tilted, it's called a smectic C. Incidentally, smectic C liquid crystal was discovered only in 1965, as we were just starting our research activity in Mysore. And Professor Chandrasekhar also initiated investigations on optical properties of cholestric liquid crystals. I think Rajaram already mentioned this in the morning. Now, 1958, we come from, I am going to say why the research work in liquid crystals picked up around the end of 1950s. Charles Frank reformulated a description of what is called curvature elasticity of nematics. See, any vector field can have only 3 types of spatial variations: play, twist, and bend. And the relevant elastic constants are extremely weak. And this is very important for the operation of liquid crystal display, as I will mention later. Next, in the late 1960s, Leslie finalized the hydrodynamic theory of nematics. You need 5 viscosity coefficients to describe the hydrodynamics of nematics because flow and orientation of the molecules get coupled. So it becomes a very complex description. And more than anything else, in the late 90s, 60s, Digens came into the field. He formulated the Landau theory to describe several phase transitions: nematic isotropic, smectic A to nematic, smectic C to smectic A, and so on. And in particular, he pointed out the analogy between smectic A to N, that is nematic transition, and superconductor to normal metal transition. I will come back to this point again later on. Another interesting thing happened around that time. In 1969, Helfrich explained you see, if you apply an electric field for a cell in which I have oriented the molecules in the horizontal direction, say, and I apply a vertical field, in certain type of nematic liquid crystals, beyond a threshold, you see a roll pattern. This is very similar to the Rayleigh-Bénard instability of liquids heated from below. Helfrich explained this periodic roll structure as arising from space charges which can accumulate due to a bend fluctuation of this orientation field. This is called an electrohydrodynamic instability. The interesting point is, if you increase this, you see this threshold is around 10 volts. If I increase the voltage to say 15 or 20 volts, then it leads to a chaotic motion in the medium. And now the medium looks like a ground glass plate. So this has a clear-cut contrast from a region in which you have not applied any electric field. So that led to the first liquid crystal display using this so-called dynamic scattering mode. And now I come to the Raman's era. 1968 was the 80th birthday of Professor Raman. So a very special Indian Academy of Sciences meeting was held in Ahmedabad to celebrate that birthday. And you see three people here. This is Professor Chandrasekhar, that one, who becomes very important for our coming story. Of course, Raman is there in the center. I must check. Again, I pressed the wrong button always. You see Professor Ramseshan there, and you see Professor M.G.K. Menon there. These two latter gentlemen played a very important role in transitioning this institute from the Raman era to the next era. This is what I understand from talking with people who know about this. In 1970, Professor Raman was not feeling very well, and the academy meeting was held in the Raman Research Institute a few months earlier than usual, maybe June or July if I am not mistaken. Professor Chandrasekhar was one of the invited speakers, who in turn asked me to briefly describe the molecular aspects of mesogens, and all this was held in the auditorium. And perhaps I am the only fellow here whom Raman heard. Of course, many of you might have heard him, but here I am. In 1971, of course, Professor Raman had died in 1970, November 20th. RRI becomes the very first research institute to be directly financed by the Department of Science and Technology. Professor Radhakrishnan was made the director, and he in turn invited Professor Chandrasekhar to develop a liquid crystal laboratory in RRI. He asked R. Shashidhar, who was about to submit his thesis, and me, who I had just got my PhD, to join him in this effort. So I joined RRI in September 1971. Few days later, Shashidhar came and Professor Chandrasekhar joined few months later for some administrative reasons, let me put it that way. Of course, we were allocated the old workshop building to be converted to the liquid crystal lab. I am quite sure you know that lab now, the ground floor. It used to be the workshop building at in the Raman era. Realizing that we needed to design our own materials to be competitive in this field, a synthetic organic chemistry lab was added, with V. Surendranath as a chemist and B.K. Sadashiva as a student. That is also a very important thing in this story. G.S. Ranganath, I think Rajaram has already mentioned, he joined later as a theorist. C.L. Ketrapal and Ajit Kova, who specialized in determining structures of small molecules which were dissolved in nematic crystals, liquid crystals, using the NMR technique. They were in TFR, they came and joined us, I think by the middle of 1972, if I am not mistaken. And in fact, this technique was itself invented by Saupe, whom I mentioned earlier, of the Mayer-Saupe theory. The first batch of physics research students were P.P. Karath, K.A. Suresh, and U.D. Chini. We could start a few experimental studies using some equipment from the Raman era. A couple of microscopes, an electromagnet which was built locally with the help of apparently Hindustan machine tools, a rotating anode X-ray generator, an infrared spectrometer, and so on. These were the equipment available to us. Twisted pneumatic liquid crystal display, which finally became an extremely important display technology, was invented in 1971 as we were moving into this institute. And to reduce the operating voltage, many new compounds with large longitudinal dipoles were synthesized. So the question then was, since now there are very large dipoles, the intermolecular dipolar interaction compares to the thermal energy. So can you get ferroelectric pneumatic? Back to Born. The answer, we argued, is no, because such molecules should have short-range anti-parallel order rather than the parallel order that he discussed. But of course, the director remains apolar because of this, but there is no long-range anti-parallel or anti-ferroelectric order because we have a liquid. Later X-ray studies in UK showed that it leads to what is called a partial bilayer structure because the strongest interaction is still between the aromatic cores of the molecules and the chains are thrown apart. Detailed theoretical and experimental studies were undertaken on the optical properties of electric liquid crystals with and without added dyes. A notable result is the analog of Borbon effect that Rajaram mentioned in the morning, and I show a figure of that original Borbon effect, where there is an additional transmission when the absorption and reflection bands match. Absorption band of the dye and the reflection band of the cholesterol. Of course, the people involved in the study were Chandrasekhar, Rajaram, Ranganath, Suresh, and U.D. Kinney. The twist elastic constant, I showed you that there are 3 elastic constants, is a difficult thing to measure using optical transmission because of what is called adiabatic theorem. I won't go into that. We used a new geometry of observation to detect this deformation and found a few results on dependence on all 3 elastic constants on the short range order in the medium, and these have been very much used by various people working in this field. Karath and I were involved in this study. S. Venugopalan had joined us as another faculty at that time. Venugopalan took his PhD with Professor Ramdas. Ramdas was a student of Raman here in this institute. And he was a spectroscopist. So he studied the far infrared spectra of several compounds, mainly rotational degrees of freedom of the molecules. High pressure studies were started in collaboration with the National Aeronautical Laboratories those days to discover pressure-induced mesomorphism. Here the people involved are, of course, Shashidhar, Chandrasekhar, Ram Seshan, and the chemicals were synthesized by Sadashiva and Surendranath. Another activity which was started was surface tension measurements across the nematic to isotropic transition in several compounds by Shashidhar and his students S. Krishnaswamy, and a theory of this was developed by Croxton, who was visiting us from some university in the UK, and Professor Chandrasekhar. So the main point there is the surface tension is supposed to go to decrease with increase of temperature, but when you come close to the nematic isotropic point, it has a dip, increases, has a maximum, and then continues to decrease. These people could account for it. I won't go through how it happens and so on. It's too long a story. Another measurement which was started was the dielectric measurements, and compounds known as cyanobiphenyls showed a positive jump of the average dielectric constant at the nematic isotropic transition. The average dielectric constant is proportional to the density, and if the density decreases, you expect the epsilon to go down, but instead it went up, and that was, of course, in accord with our theory that it's an anti-parallel orientation between adjacent molecules. Now, 1973, was the silver jubilee year of RRI, just as next year is going to be the platinum jubilee year. So a week-long school followed by an international conference on liquid crystals were arranged in December of that year to mark that occasion. Saupe, I mentioned his name, and Dijanes took part in both of them, gave lectures in the school as well, and many other very well-known scientists like Leslie and Gray, who is the chemist who synthesized these cyanobiphenyls, they were in the conference. All the results from the RRI that I listed earlier were presented in this conference. The proceedings, of course, were published as a supplement to Pramana, edited by, of course, Professor Chandrasekhar. Shape anisotropy of molecules, of course, is an essential requirement for you to observe liquid crystalline properties. Rod shapes are the simplest, but discs also have shape anisotropy. And it was thought worthwhile looking at compounds of such molecules. And indeed, these compounds were synthesized in our chemistry laboratory. This is the simplest disc-like molecule that you can think of, just one phenyl ring surrounded by 6 long chains of various types. And indeed, it exhibited a new type of liquid crystal altogether. This, using optical and X-ray studies, it was shown that these compounds exhibited what are called columnar liquid crystals. These are liquid columns, and the columns themselves in turn have a two-dimensional arrangement. So these are one-dimensional liquids and two-dimensional crystals, unlike the spectic phase, which are one-dimensional crystals and two-dimensional liquids. So this is an altogether new type of liquid crystal, and this is the most important discovery of the liquid crystal lab. And the results were published in Pramana. Chandrasekhar, Sadashiva, and Suresh were the authors back in 1977. Perhaps from Pramana at least, it is the most highly cited paper, about 1,300 or so and counting. A few thousand disc-like mesogenic compounds have now been synthesized all over the world. Both nematic and different types of 2D lattices of liquid columns are now known, rectangular, oblique, etc. Films made of vitrified nematic phase made of disc-like molecules have been used to improve the uniformity of contrast of twisted nematic displays. I told you twisted nematic has a 90-degree twist. So you apply an electric field, the molecules lift up in one quadrant. So if you look down this direction, there is a certain type of optical anisotropy. But if you look from an orthogonal direction, the optical anisotropy is very different. So the contrast will be very non-uniform. And since the disc-like molecules have the opposite anisotropy compared to the rod-like molecules, they have been used to compensate for this. The columnar structures with suitable molecules also exhibit high anisotropy of electrical conductivity, and they have been studied for that application. The other most important thing that happened in 1977 was the publication of Professor Chandrasekhar's book. It's extremely well received by the community, and it was published, of course, by the Cambridge University Press. And a second paperback edition has since been published. Russian and Japanese translations have also been published. Of course, since there is an application, out of curiosity, we made some DSM and TN liquid crystal displays in the lab. Some engineers from BEL visited us. Some of them got the scent, and proposed that we collaborate with them for developing an indigenous know-how for producing liquid crystal displays. We got into, that was anyway a public sector organization, so we got into an informal understanding with them to do that. And in fact, we did that, and in the 1980s, BEL had a pilot scale production of simple twisted nematic displays, for petrol bunks, railway station displays and so on. And some of the older people here might have, if you went to that old Palam airport those days, you would see a huge display board made by BEL to show the departure and arrival timings of planes. But then, what has happened since then? Of course, this was back in 1980 or so. Active matrix displays, in which each pixel is backed by a thin film transistor. Oh, sorry, I make the same mistake every time. You see, TFT is a thin film transistor which backs each pixel. This has a major advantage over the passive displays, especially for color displays. So the required R&D was extremely expensive, and BEL said, we can't do it. So that's all. I think something happens when I put my hand down. Anyway, it always goes back. And then what happens about 30 years ago, I am jumping to 1990s because I want to finish our association with displays. I think after 1990, Aeronautical Development Agency, which was the nodal agency for the light combat aircraft, they approached me for help in selecting a suitable product for the cockpit display of LCD. And then, they had brought several quotations from various companies abroad. I suggested to them that they should explore with BEL instead to develop it locally. Of course, this was done, and I think they are the nodal agency still giving the cockpit displays, but with imported active matrix LCD. So, LCD era in BEL came to an end around that time. They are no longer producing. And still, in the application side, T.N. Rukmangathan had joined us as an engineer. I think he is here. And we started exploring the possibility of selecting all rows of a passive matrix LCD simultaneously, instead of the prevalent line-by-line addressing scheme at that time. This so-called binary addressing technology had a lower contrast. And later, he developed what is called IHAT, improved hybrid addressing technology, to overcome this problem where a few lines are addressed at a time, not all the lines. Multi-line addressing schemes were used in cell phone displays. Of course, these are variants of this scheme of Rukmangathan, till the active matrix displays became affordable, and now probably everything is active matrix. Of course, Rukmangathan has authored a book on addressing techniques of LCDs recently. F.C. Frank of Frank Elasticity visited us for a few months in 1979 to 80. And an international conference was organized in December of 1979. Around that time, the type of problems we were doing were the following. Ranganath, for example, explored the interactions between line defects in pneumatics and showed that anisotropy of elasticity leads to angular forces between them. And this is a photograph not taken by us, I think, of a holistic liquid crystal where the disclinations twist around each other due to this effect. Kinney undertook a very systematic effort to explore flow patterns in pneumatics in various cell geometries, 5 viscosities, 3 elastic constants, and only a person like Kinney, I think, can do it. It's a very tough problem, generally. Many new compounds with cyanoid groups were synthesized, and their physical properties were investigated. Some of these compounds were found to exhibit, I'll come to what are these a little later, but let me say it anyway. Re-entrant pneumatic, pneumatic to pneumatic transition, smetic A to smetic A transition, and so on. Now I come back to the electrohydrodynamic instability that I mentioned earlier. The wave vector of this instability you can expect purely on general grounds should be parallel to the undistorted director field. But actually, There are many studies which showed that there was a non-zero angle between them. So this problem sort of interested us, but to explain that I must first describe another property of nematic liquid crystals. Though the nematic has an apolar order, splay and bend distortions, splay is like that, bend is like that, they are obviously polar. So these can exhibit polarization. This is called flexoelectricity, splayed and bent nematic liquid crystals. In fact, the original proposal was by R.B. Mayer, who wanted dipoles, but later Pro and Marcero showed that you don't even need them, because quadrupoles with a splay distortion give you a dipole density. The picture is clear, I suppose. Now we show that flexoelectric contribution has to be taken into account in order to account for this result, that there is an angle between N naught and the fact that there is an angle between N naught and the wave vector of that instability. I think Raghunath and I were involved in this work. Of course, we realized that not many flexoelectric measurements are available, because if you apply a DC field, it is usually screened by ionic impurities. So we developed then an AC technique, electro-optic technique, which required a very detailed numerical analysis. Shobha Warrier and I were involved in this work, and this technique was later used by the Japanese and others to measure flexoelectric coefficients. Some compounds with the cyano-end groups exhibit the following phase sequence as you cool it: isotropic phase, nematic phase, a smectic AD phase with a partial bilayer structure that I mentioned. Cool it further, it goes back into a nematic. This is called a reiterative nematic. You cool it further, it goes to another smectic phase, smectic A1, with a layer spacing which is equal to the molecular length. So how does this arise? So I was obviously interested in the molecular origin of this. We pointed out that as the polar molecules approach each other, see, this is the anti-parallel arrangement that I talked about earlier, but I think probably this is run out of battery, most probably. And on the, Anyway, I think I can as well stand here, right? You see, I already pointed out the anti-parallel arrangement where you have a layer spacing which is longer than the molecular length. Now, our point was, as you bring the molecules closer, the chains start interacting. Here the chains don't. And that goes as 1 over r to the power of 6. But then there is a repulsive interaction between the dipoles, but this dipole induces a dipole in this which is opposite to it. The induced dipole reduces this repulsive interaction, and that also goes as 1 over r to the power of 6. Whereas pure dipole goes as 1 over r cube. So as you cool, you favor this. Therefore, is smectic A1 ferroelectric? Unfortunately, no, because the residual dipolar interactions are still long range. So what happens is a few molecules orient this way, then it goes the other way, and so on. So it forms what is known as smectic A tilde phase. Experimentally, this was studied in France more than us. Anyway, now we come to, I go back a bit. In 1975, Mayer demonstrated that smectic C star means the molecules are chiral. Smectic C means the molecules are tilted in the layers. So smectic C liquid crystals with tilted molecules, and the molecules being chiral, can exhibit in-plane polarization along the normal to the tilt plane. Due to symmetry reasons, I advise you to see how it occurs yourself. And this can be switched from one state to another by applying a strong electric field. See, the pneumatic couples with the external field because the conjugate field to the order is E squared, not E. Ferroelectric, the conjugate field is E. So I can apply an opposite field as strong as I like and make it switch very fast. This created a big fuss in the field of liquid crystals. In fact, so much so that they had to start an altogether new series of international conferences every alternate year just to handle the number of publications, papers, and people working in the area. Sadashiva, of course, and his students synthesized many compounds and their properties are studied in the lab. Ratna, Kenneth, Krishna Prasad, and many others were involved in these studies. Smectic C star also exhibits a helical structure because the molecules are chiral. And therefore, the pitch of the helix can become of the order of the wavelength of light and exhibit some unusual optical properties as well. So, the optical properties both for light propagation along the helical axis and in the phase grating or the Raman mode were also investigated, both theoretically and experimentally, and this included some dynamic light scattering studies by Suresh, Ranganath, and Yuvraj Shah, if I am not mistaken. The 9th International Liquid Crystal Conference was supposed to be held in Poland in July 1982. Of course, Russians, who were happy to invade other countries, had invaded Poland at that time. And therefore, ILCC had to be shifted out of Poland. Professor Chandrasekhar agreed to organize it, but not in July. Obviously, it was not possible, but only in December of that year in Bangalore. And of course, it was held in Hotel Ashok because we had several hundred participants, 3 parallel sessions, and so on. In 1983, Professor Chandrasekhar was elected to the Fellowship of the Royal Society. And when the International Liquid Crystal Society was formed later, he was chosen to be its inaugural president. Of course, he has received a number of awards. I won't list them here. And coming back to smectic C, in some compounds, the smectic C phase can occur on cooling either directly from the pneumatic phase or with an intermediate smectic A phase. In one system, the NAC multi-critical point was located in the pressure temperature phase diagram, and very curiously, its topology that you see here was exactly the same as the concentration temperature diagram, which was seen earlier by others. So that's another highlight of the pressure studies made in RRI. Now, the question is, why do the molecules tilt in the first place in this smectic C liquid crystal? This was led to a lot of, very confusing papers, and then we suggested the following. See, supposing the lateral dipoles, these were known to exist in all compounds forming smectic C phase. Everybody took it on the axis, but if you looked at the chemistry, chemical structure, they are never on the axis. They are always off axis. If you just used it, then in the smectic A phase there will be a repulsive interaction because the two come very close to each other in this configuration as the molecules rotate freely. One way of escaping that is to push one molecule with respect to the other, and if you do this to everything, it becomes a smectic C. So this theory we developed, and I think, I don't remember the name, but anyway, Govind was my part-time student at that time, and I developed this theory. And that's the only sensible theory up to now. In 1990, Venugopalan, V Surendranath, and Shashidhar had migrated to the United States, greener pastures. C.L. Ketrapal had shifted to the Institute of Science, and Ajit Kunwar had shifted to Hyderabad. And in 1990, Professor Chandrasekhar retired from RRI, and he started the Center for Liquid Crystal Research, CLCR for short, in a building provided by BEL. And a couple of years later, V Lakshmi Narayan, who was an electrochemist, who was working with the astronomy astrophysics group, he was transferred to our lab because he was a chemist and we had a chemistry lab, so it was a good move to get him. And he worked on many electrochemical systems with his students, and perhaps he is also well known for his construction of a scanning tunneling microscope locally. In 1989, a Japanese group discovered that some chiral compounds undergo the following sequence of phase transitions as you cool. Start with isotropic, go to smectic A, then something called smectic C alpha, which has a very short pitch, then smectic C star, the usual smectic C star that I talked about. Then if you cool it down further, it goes through two ferrielectric phases where the polarization is smaller than in the ferroelectric phase. Finally, to a smectic Ca phase in which the molecules tilt in opposite neighboring layers, molecules tilt in opposite directions, so the net polarization is zero. And they proposed, with some Japanese theorists, that this should correspond to what is called ANNE model, axial next nearest neighbor Ising model, where the dipoles can take only two possible orientations. But of course, smectic layers are liquid layers, so you can't say that they can take only two orientations. So Arun was a student at that time. Arun Roy and I, we developed what is called an XY model, which of course exhibits all the sequence of phases shown by the experimenters, and also we could calculate what happens if you apply the electric field, compare it with experiments and so on. So that's the work towards the end of 1989. Perhaps the most important phenomenological theory of design was based on the recognition of the close analogy between nematic smectic A and normal superconductor transitions. And people say when he got the Nobel Prize a few years later, it was only after the corresponding liquid crystal was discovered. The detailed theory was done by Ren and Lubensky. They showed that this should result in what is called a TGBA phase, whose structure I show here. You have smectic blocks which twist across grain boundaries made of screw dislocations. I'll just leave it at that. This is like the penetration of magnetic field in a type 2 superconductor. Take it at that level. And then a UTGB C star phase, C phase was found by others where the molecules tilt, and we found in a mixture what we call the UTGB C star phase. It's a new type of liquid crystal, the most complex TGB phase. Pramod, Pratibha and I were involved in this experimental study, whose structure I show here. It is along all three directions, but I will not. I think this is happy to go in one direction but not in the opposite. Yeah. So with Yashodhan Hatwalne, we also proposed a phenomenological model for the stability of this phase. The activity that was taken up was the investigation of 2D phase diagrams using Langmuir films. It was initiated by Suresh. I will cut short my description. I am running out of time. While most of this work was on thermotropic liquid crystals, after Raghunathan joined, he started work on lyotropic liquid crystals. In particular, I can point out the ripple phase, about which they not only did the experiments and found something new, but also developed a theoretical model. 1998 was the golden jubilee year of the Raman Research Institute. And we organized a school followed by an international discussion meeting in the December of that time, and the proceedings were published in Pramana as usual. In 1996, a Japanese group discovered that compounds with bent core molecules can also exhibit liquid crystalline phases. And we discovered a new liquid crystalline in that by making mixtures of rod-like and bent core molecules, both synthesized by Sadashiva. I will simply say it's a smectic AB phase, which is a biaxial smectic A phase. I'll skip other details. And 25th anniversary of the discovery of the columnar liquid crystal was in 2002. Sadashiva organized a 3-day international meeting, again published in Pramana. Sandeep Kumar joined us in 2002. His main interest was in disk-like molecules. He has written a book, several articles on this subject. Again, I will skip. Professor Chandrasekhar passed away in 2004 after a brief illness. He started liquid crystal work in the University of Mysore, founded the LC lab in RRI, and after his retirement from RRI, started the Center for Liquid Crystal Research. He was principally responsible for putting India on the map of international liquid crystal research. So I will skip most of this because and I will now come to the character, the more recent character of the laboratory. It has become a soft condensed matter laboratory with wider interests. Ranjini is interested in rheology of complex systems. Pramod has set up a laboratory for mechanical measurement and polymers of biological interest. Vikram Soni interested in pulling biopolymers through nanopores. Then Sayantan has been studying jamming transitions and so on. I understand all this work is going to be presented in detail in the next few days, so I will not make any comments on those. During the past couple of decades, the main international effort in the field of thermotropic liquid crystals is on BC molecules. And I will again, these are two interesting results got in the liquid crystal laboratory. One by Pratibha and her student, the other was by Malkar and Arun Roy. So they continue to work on compounds made by Sadashiva, incidentally. And Yashodhan and Madan Rao were involved in a collaboration with Sri Ramaswamy in developing the theory of a rheological response suspension of active particles. And Sri Ram, as you know, is a pioneer in this field. And Yashodhan also collaborated with Muthu Kumar in developing a theory of chiral symmetry breaking in polymer crystals and also in some liquid crystals that we had found in the lab. I will skip this. This is my own work, so I'll skip all this, except to say that finally, 3 or 4 years ago, ferroelectric pneumatics have been discovered, after all. You remember 1916, Born had predicted this. So these people said, okay, Born predicted, now finally we have the ferroelectric pneumatic. But then I had to point out, this is not the ferroelectric that Born predicted, something very different. I will not go through this because this was published last year in PRE, those who are interested may. So this arises because of a very specific charge density distribution along the length of the molecule. Only very special distribution can give rise to this. I have argued the reason for that. You see, in last few years, several faculty members have retired. Rukmangadan, Lakshmi Narayan, Pratibha, Yashodhan, Raghunathan, Sandeep Kumar. Most of them were working on liquid crystals, and the implications are clear. 2 years ago, my colleague and a very good friend Sadashiva passed away, and very fittingly, Liquid Crystals Journal has brought out a special issue in his memory. And I will not go through some missteps that we made. I thought any evolution's missteps must also be related, but the chairman is very unhappy with me, so I will simply say the laboratory continues to evolve, and my own suggestion as a white-haired person is that in a small research institute like RRI, it is better not to diversify too much. Concentrate on a few main topics and push hard on those. Then you make a mark. Thank you.